Hello, everyone. I'm Hengjie Wang. I'm a postdoc in CCSE. Today, I'm going to share about my research on transferable flow prediction with machine learning. Now, before I go to a machine learning model, I want to first introduce about how do we do flow simulation with conventional computational fluid dynamics. Now, if we want to get the flow over this airplane, typically we need to first discretize the space with a grid. And then we solve the governing PDEs on the grid to get the variable distribution over the airfoil. Now, this is usually a very time-consuming process because we need to solve complex PDEs on a huge number of grid cells. And we also need to do that repeatedly for many iterations. And also for real engineering applications, we need to consider different shapes of airfoils and different velocity, temperature conditions. All those factors can add up to thousands simulations, and each of them can take from hours to days. So you can imagine it is very time-consuming to do numerical simulations in engineering. Now, with the development of machine learning, we want to replace those expensive simulations with faster flow predictions. I'm going to show how this works with a simple benchmark. Now, in this benchmark, we have a lead-driven cavity. We know the boundary conditions, and we want to know the flow inside the box. We can solve this with conventional numerical methods that usually take from minutes to hours, depending on the accuracy. We can also train a neural network, and the neural network can predict the flow just within seconds. Now, for this simple benchmark, both of the methods can give us comparable accuracy. The reason why the prediction of a neural network is super fast is because of its simple structures. So a neural network is basically a stack of layers, and the computation associated with each layer is just a simple matrix and vector multiplication, which is very easy to run in parallel. So the overall neural network prediction has much less computation cost than solving the PDEs. Now, although the prediction of the neural network is very powerful, but to train such a neural network with high accuracy is also very time consuming. I'm going to show this with solving the boundary value problem as an example. Now, if we want a neural network to approximate the solution to this PDE system, the neural network will have multiple layers, and each layer will have some parameters. Once we have the output from the neural network, we can define a loss function, which includes the error in satisfying the boundary conditions and the error in satisfying the PDEs. We can also generate the exact solution and compare the error between the output and the exact solution. Now, once we have this loss function, we want to do a numerical optimization to find the optimal parameters that can minimize this loss function. So if this loss function equals to 0, that means we found the exact solution satisfy all the constraints. So in practice, we want this loss function to be as small as possible. That usually takes a lot of training steps. The training can also be very expensive because of the large data sets. If we want to improve the model's accuracy, we have to generate a huge amount of data. And also, we need to constrain the PDE in training the network. That will introduce a lot of computation cost. So in general, the prediction of the neural network can be super fast, but the training of the neural network is usually more expensive than the numerical simulation. Now follow this logic. If we want to get the most of a neural network, we would like to train it only once and use it in as many cases as we can. But unfortunately, the state-of-the-art neural network trained in this way will be specific to the boundary condition and to the domains. That will really limit its application, and we cannot use it as many times as we want. So at this point, we want to argue that in order for the neural network to be efficient, we need to make sure that the flow predictions are transferable. So by transferable prediction, we mean that the neural network trained on small domains like this should be able to predict flows in larger domains of different shapes and different boundary conditions. And for the rest of this presentation, I'm going to show our solutions to this end. So we propose a transferable machine learning framework, which is called Mosaic flow. It follows the divide and conquer strategy. It has two components. Well, the first component is called GFNet. Here we train a neural network that can predict the solution on a small square domain. we define this small square domain as one genome. And the GFNet will take in the boundary condition on a genome and then predict the solution for this genome. And in our framework, this GFNet is only trained once. The second part of our framework is called IMF Predictor. So it's going to assemble GFNet's prediction to make up a solution for a larger unseen domain. And at this step, we don't have to retrain the model. Now, before I went to more details of our framework, I want to first talk about how, in general, this divide and conquer strategy works for solving PDEs. Now, assume that we want to solve this PDE in this rectangular domain. This is actually equivalent to solving the same PDE, but in two smaller genomes. The only difference is that the boundary condition of this blue shared border is unknown for both genomes. So the question is, how can we update the shared border? Now, there are usually two methods. The first method is that we get some initial guess on this shared border, and then we solve the PDEs in both genomes. And then we use the solutions to update the value on this shared border. Then we do this iteratively. This will converge to the exact solution. And the second approach is called Schwartz method. It's going to introduce an auxiliary genome. So it starts the same as using the basic genomes. We get a solution of those two small blue genomes, but we use their solution to update the boundary condition of the auxiliary genome. Then we solve the PDE again in this auxiliary genome to get the solution on this shared border. We can do this iteratively, and it's also going to converge to the exact solution. The benefit of Schwartz method that it can significantly speed up the convergence. Now, for this particular example, we see that using the auxiliary genome can reduce the number of iterations to convergence by 1 order of magnitude. Next, I want to show the details of our framework. So the first component is called GFNet. The input of this neural network have two parts. The first part is the discretized boundary condition. It's the values at the boundary point, which is shown by this blue dot. And the second part is the coordinates from one point that is inside the domain. And our neural network will approximate the solution in this genome. We choose the architecture of the GFNet based on the type of the PDEs. So if the PDE is linear, like a Poisson or Laplace equation, then at the last layer, we use a vector dot. This will make sure that the dependence of the solution on the boundary condition is also linear. Now, if the PDE is nonlinear, like the Navier-Stokes equations, we will combine the two parts of the input and let them pass through all the nonlinear layers. Now we need to generate enough data to train our GFNet. Here again, we choose different data generation methods based on the type of PDEs. For simple PDEs like the Laplace and the Poisson equations, we know the solution will exist for smooth boundary conditions. We can sample random functions as our boundary condition. Now for more complex PDEs like the Navier-Stokes equations, their boundary condition have to satisfy some constraints, like the mass and the momentum conservation. We cannot use random functions. In this case, we will run some numerical simulation first and then extract our training data from the solution. The second component is IMF Predictor. It's going to combine GFNet's prediction and assemble it into a solution for larger domains. We demonstrate this using an example that is 4 times larger than our genomes. So the first step is to divide the domain into basic genomes. And then using the Schwartz method, we are going to add auxiliary genomes to cover the shared borders. And in our case, we also add 1 genome to cover the shared corners between the basic genomes. And then we update all the genomes per iteration in this order. And we can see that initially we have some large error near the shared borders because their boundary condition has not been found yet. But after iterations, the error will decay and eventually the prediction will converge to the exact solution. We want to evaluate our problem by first solving the linear Laplace equation. Now in this case, we consider 2 different boundary conditions that has not been used in our training. And in our training, we only let the model sees domain that have a unit size, and in our test, we want to scale up to domains that is 64 times larger than our training genome. Here we are compared with PIN. PIN stands for Physics Informed Neural Network, which is kind of the state-of-the-art used machine learning to predict PDE solutions. Now, accuracy-wise, we can see that for one of the boundary conditions, as we increase the size of the domain, PIN actually blows up. Well, for our model, we can maintain the accuracy at a stable level for different size of domains. Now, performance-wise, we are orders of magnitude faster than PIN. Well, this is because PIN is not a transferable model. So each time it sees a domain of different size, it have to retrain the model again. The training is very expensive. But our model, we don't have to train the model. That's where this benefit comes from. And next, we want to challenge our model to some extreme case. So here we consider a domain that is more than 1,000 times larger than our genome. But this domain have curved boundary. But our genome can only be a small square domain. So in this case, we first downgrade the curved boundary into a mosaic presentation. And then we use our model to predict the solution. We can see that even for domain of this large size, we can still get a fairly accurate prediction compared to the exact solution. Next, we want to test our framework on nonlinear PDE systems. Here we choose the Navier-Stokes equation. Now we train our model on small genomes of size 0.5 by 0.5. And again, we want to predict flows in larger domains of different shapes. So our first test with the Navier-Stokes systems, we chose a domain that is 4 times larger. And this domain will have similar flow features compared to what we used in training, but with a different boundary condition. Now we see that when we use 9 genomes, which is the same number of genomes we used in the Laplace equation, the solution is not accurate enough. Well, this is because the Laplace equation is a linear equation, and here we are facing with a nonlinear system. So the dependence of the solution on the boundary condition is much more complex. So we need to increase the number of genomes, and we can see that significantly improves the accuracy. Now we have a fairly accurate prediction compared to the exact solution. Here we also compare with PIN. The PIN model here is trained for a constant boundary condition, and we let it to predict for an unseen boundary condition. We can see the prediction is completely off. This again confirms that PIN is not transferable across different boundary conditions. And next, we want to choose a more challenging case. So here we put an object in the flow field, and that object have a sharp corner. So this is some feature the training data set does not include. Now we can see that our framework can still capture the major flow features like the 3 large vertices, but at the same time, it also have a relatively large error at the sharp corner. Well, besides this, the error at the sharp corner, we also notice some error near the wall boundaries, because here the streamline should be parallel with the boundary. This is called no penetration boundary condition. But our streamline is normal with the boundary, so this is not physical. Well, this error is because our GFNet does not enforce the boundary conditions. And this is in fact a common error in machine learning based models. Because if we go back to the way that we define the loss function, so the boundary condition appears in the loss function. And in practice, we cannot reduce the loss function to 0. So it's only a small value. That means there will be some errors in the boundary condition. Now to overcome this, we separate our prediction into 2 parts. So the first part is a function that strictly satisfies the boundary condition. And the second part is the neural network. Then we apply a filter, and this filter will remove the neural network's error on the boundaries. So in this way, we can enforce the input boundary condition. And with this improvement, we can see that now the streamlines are largely parallel with the wall boundary. So that shows the enforcing the boundary condition can actually help to preserve the physical meaning of the flow. Now, the Mosaic flow framework is mostly the work done during my PhD program. Now in CCSE, my ongoing work involves combining this machine learning framework with AMREX. So AMREX is a framework for adaptive mesh refinement, which is developed at CCSE. It has a wide range of applications from multi-phase flow simulation to astrophysics. So the basic idea of AMREX is to discretize the domain with boxes, and the boxes can potentially overlap with each other. So in that sense, it's very similar to our concept of genomes. And I'm trying to combine Mosaic flow with AMREX so that we can speed up the numerical simulations. And another thing I'm interested in is to speed up the convergence of the Schwartz method. So we use the Schwartz method to find the proper boundary condition on the shared borders. Now, the benefit of Schwartz method is its robustness, and mathematically it's guaranteed to converge. But the downside is that computation-wise is an iterative approach and it's kind of inefficient. So the other way to look at the Mosaic framework is that it can reduce the number of unknowns of the original problem into the unknowns only on the shared border. That usually means reduce the number of unknowns by 1 or 2 orders of magnitude. So it's kind of a very powerful reduced order model. But maybe instead of the Schwartz method, we can use some classic numerical optimization skills that used for reduced order models, and that hopefully can speed up the convergence. Now, to summarize, in this presentation, I introduced our transferable machine learning framework for flow predictions. Here, the neural network only need to be trained once, and we can use it to predict flows in unseen domains with different sizes and different shapes. Now, at the end of my presentation, I want to thank my collaborators. Professor Aparna is my PhD advisor, and Ramin is a professor from University of California, Irvine, and Robert is his graduate student. We work together on this project. So if you want to find more details about our project, we would like to refer you to this paper. It also includes the open source code of our framework. And thank you so much for your interest. I'm happy to take any question. Thank you.